I want to start with something that seems completely obvious. Light propagates, right? You turn on a lamp and the light comes out of the lamp, hits the wall, and you see the wall. Simple. The light traveled. We've known this for centuries, but what I want to do today is the following. I want to look at this word, travels, very closely. Because when you really sit down and ask, what is traveling? What exactly is moving? You find yourself at the center of one of the most beautiful and disturbing stories in all of physics. And I realize that the things that seem most obvious are almost always the ones that most deserve to be investigated deeply. So let's start with what your intuition probably already tells you. You probably imagine light as something similar to a wave in water. You throw a stone into a lake, ripples appear. The ripples spread outward, and that's traveling. Something is in motion. Now, in water waves, the water itself is moving, not from one shore of the lake to the other, but up and down. The wave is a pattern of disturbance moving through a medium. The medium is water. The wave pattern moves forward. The water stays more or less in the same place. So, naturally, people in the 19th century said, well, light must work like that. It's a wave. Therefore, there must be some medium, something for it to ripple through. They called this the ether, and it was a perfectly reasonable conclusion. Waves ripple through something, right? So light waves would also need something to ripple through. Then came the Michelson and Morley experiment in 1887. They built an extraordinary device, an interferometer, capable of measuring tiny differences in the speed of light in different directions. You see, if there is a stationary ether and the Earth is moving through it, then light traveling in the direction of the Earth's movement should be a little slower than light going perpendicular to that movement. It's like rowing a boat against the current versus rowing across the river. They measured this with great precision, using the best equipment available at the time, and they found absolutely nothing, no difference at all. That was the first shock. The ether simply didn't exist. Light didn't wave through anything. It waved in the vacuum. That alone should keep you up at night. What oscillates if there's no medium? We'll get back to that. Maxwell had already given us the answer, in a way, about 20 years earlier, even though no one had fully understood what he was saying. Maxwell wrote a set of equations, 4 of them, Maxwell's equations. And from these equations, he showed that electric and magnetic fields can sustain each other. A changing electric field creates a magnetic field, and a changing magnetic field creates an electric field. And these two fields chase each other through empty space. And they do this at a specific speed, the speed of light. He calculated this value using only the constants of electricity and magnetism. And he got 300,000 kilometers per second, exactly the speed of light. And he wrote essentially that it seemed possible to conclude that light is an electromagnetic disturbance. That's already strange. What oscillates is not matter. What oscillates is the field. An electric field and a magnetic field oscillating perpendicular to each other, perpendicular to the direction of motion, chasing each other through space at 300,000 kilometers per second. Nothing material moves forward. The disturbance moves forward. The values of the field change. No substance is transported. But then, and this is where things actually get fascinating, Einstein appears in 1905 and says something that at first sounds like a fix, but is actually a revolution. He says that the speed of light is identical for all observers, regardless of the speed at which they are moving. You could be standing still. I could be on a spaceship at half the speed of light. We both measure a beam of light moving exactly at 299,792 meters per second with no difference at all. That's not intuitive. If I throw a baseball at 90 miles per hour and you're coming toward me at 60 miles per hour, you measure the ball coming at 150 miles per hour. That's just addition. That's Galileo. That's how normal things work. But light doesn't work like that. You can run toward a beam of light and it still reaches you at exactly the same speed, always in every circumstance. And what this means, and Einstein realized this, is that space and time are not separate and independent things as we imagined. They are connected. They are parts of a single thing, space-time. And when you start to move, space and time swap in a way that keeps the speed of light constant for everyone. Time slows down for observers in motion. Lengths contract. This isn't science fiction. It's measured daily in particle accelerators. The muons created in the upper atmosphere should decay before reaching the ground. By classical calculation, they wouldn't make it. But they do make it because time runs slower for them. We measured that. Now, from the photon's own point of view, things get even more radical. In the photon's frame of reference, if you could travel along with a photon, which isn't possible, but just imagine it as a thought experiment, time simply doesn't pass. The photon leaves the sun, travels 150 million kilometers to Earth. It takes 8 minutes by our clock, and for the photon, those 8 minutes are zero. It is emitted and absorbed instantly. The distance it travels from its own point of view is zero. It doesn't experience any journey. It doesn't experience absolutely anything. It blinks out in one place and appears in another, with no interval of time between the two. I think that's extraordinary. We say that the light traveled, but from the photon's perspective, there was no journey at all. Now, I need to tell you something important about what I just said, and what I always say, and what every honest physicist needs to say. When I described the photon's perspective, I was imprecise, because the word perspective presupposes an observer, and a photon has no mass. And special relativity collapses when you try to transform to the reference frame of something without mass. You simply can't travel along with the photon. The math doesn't allow it. So when I say from the photon's perspective, I'm extrapolating something that the math suggests, but doesn't fully allow. That's a fundamental distinction. Physics is about what the equations say, not about the stories we tell about the equations. Stories are useful, but they're not the same thing as physics. Okay, so we've already established that light is an electromagnetic wave. It travels through empty space without any material thing moving, and it travels at a speed that is constant for all observers. And in its own frame of reference, if we use that term a bit loosely, no time passes. But now I want to get into the part that I think is the most beautiful and the most disturbing. What quantum mechanics says about all of this. At the beginning of the 20th century, something was bothering scientists, specifically the photoelectric effect. You shine light on a metallic surface and electrons are ejected. All right, but here's the problem. The energy of the electrons that come out doesn't depend on the brightness of the light. It depends on the frequency and the color of the light. Intense red light doesn't eject any electrons. Weak blue light ejects electrons just fine. A wave picture can't explain this. If light were a wave, more brightness would mean more energy, and you would expect that more intense light would eject electrons with more force. But that's not what happens. Einstein, in 1905, the same year as special relativity, an extraordinary year for him, states that light arrives in packets, quantized blocks. Each packet carries an energy that depends on its frequency and is equal to h times nu. H is Planck's constant, nu is the frequency. A single packet has enough energy to eject an electron, or it doesn't. More brightness just means more packets, not more energy per packet. If each packet isn't energetic enough, no electron will be released, no matter how many packets you send. We call these packets photons today. And here the story becomes genuinely strange, because now light is not just a wave, it's also a particle, discrete grains. You can detect them one by one. A very weak light source fires photons individually. And if you have a detector that's sensitive enough, you get click, 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 separate events, individual portions of energy arriving, not a continuous stream, clicks. But what's disturbing is the following. If you take these individual photons one at a time and make them go through two slits, the famous double-slit experiment, each photon goes through both slits at the same time. Because when you observe where they land, even one photon at a time, over time you build up an interference pattern, stripes, an alternating pattern of where the photons arrive and where they don't. Exactly what you would get if waves were passing through both slits and interfering with each other. But we're sending one photon at a time. There's nothing to interfere with it. The photon interferes with itself. And if you put a detector at the slits to detect which slit the photon actually went through, the interference pattern disappears. The photon now goes through one slit or the other, like a normal particle, and you get two groups instead of a wave pattern. The act of finding out which slit it went through destroys the interference. This left Einstein upset. He never accepted it. He thought there should be a deeper explanation. He used to say that God does not play dice. And yet, the theory works. It predicts everything we measure with greater precision than any other theory in the history of science. Quantum electrodynamics, the quantum theory of light and matter, is the most rigorously tested theory in physics. Its predictions have been confirmed to as many as 10 decimal places. So what is light really? A wave or a particle? And here I want to tell you something I've said before, and I repeat it because I consider it fundamental. It is neither of the two things. It's something for which we don't have an adequate word or a satisfactory classical image. The words wave and particle are human inventions, based on human experience with macroscopic objects, water waves, billiard balls. Nature at the quantum level is not obliged to fit into these words. It acts in its own way. It's something photonic, a category of its own. What we have is a mathematical structure, probability amplitudes, complex numbers, wave functions that correctly tell us the probability of finding a photon anywhere and at any time. The wave function is wave-like, it has frequency, wavelength, and it interferes with itself. But when we actually detect a photon, we detect it at a definite position as a particle. Where the wave function has a large amplitude, it is more likely to be found. Where it has a small amplitude, it is less likely. And when we detect it, when someone looks, when a detector clicks, the wave function collapses at that point. Now I need to tell you something about this image that I find absolutely dizzying. In my classes on quantum electrodynamics, I described how a photon goes from point A to point B, and here's the honest picture, the correct picture according to quantum mechanics. The photon doesn't just follow a straight line. It takes every possible path, every imaginable path from A to B at the same time. Completely absurd paths, curved, zigzagging, paths that go all the way to Jupiter and back. All of them. Each path contributes a small arrow, an amplitude. And you add up all the arrows. Most of them cancel out because neighboring paths point in random directions and cancel each other out. But the paths close to the classical straight line path, close to the minimum time path, those don't cancel out. Those arrows by chance point roughly in the same direction. So they add up and produce a significant total contribution, and the result is that the photon overwhelmingly behaves as if it traveled in a straight line, because that's where all the contributions add up without canceling each other out. This is called the path integral formulation, and it reveals something profound. The classical picture that light travels in a straight line is not a rule that light follows. It is the emergent result of quantum mechanics, where all the wild quantum paths cancel each other out, and only the classical path survives. The law of reflection, the law of refraction, the straight line propagation of light, all of that emerges from there. Light moving in a straight line isn't a fundamental law. That's what happens when you add up all the arrows. Now let me put all this together because I want to be transparent with you about what we know and what we don't know. We know something travels from a source to a detector. We know that this happens at a fixed speed, c, in a vacuum, for all observers. We know that what propagates has wave-like properties, it has frequency, wavelength, and it interferes with itself. We know that it has particle-like properties. It arrives in discrete portions as clicks in a detector, carrying a defined energy equal to h times its frequency. We know that a photon has no mass, and because of that, it can only move at the speed of light, never slower, never faster, in a vacuum. We know that, from a relativistic point of view, the photon's proper time is zero. It doesn't age, it doesn't experience duration. What we don't know, what I won't pretend to explain to you, is what really happens between emission and detection, what the photon is doing when no one is observing. Is the wave real? Is the particle real? Is there even a trajectory? These questions, and I want to make this clear, might simply not make sense. They might not have answers, because the answers we get depend on how we ask the question, on what setup we use. Nature isn't secretly doing something and hiding it from us. The question, which slit did it actually go through? It might simply have no answer when we don't look. This isn't a limitation of our knowledge. It could be a feature of reality itself. And that's what I mean when I say that nobody understands quantum mechanics, not because the equations are confusing, they actually aren't, but because the equations don't provide a story, they provide a calculation. You enter your question, you get your probability, and the probabilities are correct. But if you ask what happens in between, you don't get an answer, you get philosophy. And I'm always suspicious of philosophy where there should be physics. So here's the reality check I wanted to give you. Does light travel? Yes. At 300,000 kilometers per second? Yes. Is it a wave? Yes. Is it a particle? Yes. Is something physical in motion? Well, the values of the fields change. The electric and magnetic fields oscillate, but no material substance is transported. Does time pass during the journey? Not in the photon's frame of reference, which we cannot strictly adopt, but in the limit, no time passes. Does the photon follow a straight line in the sense that it adds up correctly in quantum mechanics? Yes, but only because all the other paths cancel out. And what is light? It's a quantum of the electromagnetic field, a photon, something that is both wave-like and particle-like, and neither at the same time. That travels without needing a medium, that moves at the only speed allowed to it, that simultaneously takes all possible paths, and for the most part, it cancels itself out. And that arrives as a click. That's what a journey looks like when it's nature making it happen. And I think that's much more interesting than the simple answer. Don't you think?